All right, so first up are titrations, which we've done in lab already or will do, and you'll do plenty of those at your time here. Titrations, we generally use a burette, right, to accurately measure how much of a compound we've dispensed. And the basic idea of a titration is to use a known concentration of something. Concentration is a big word, so I'm just going to abbreviate it with brackets. So if you ever see brackets, that means concentration. And the known concentration, what's known as the titrant, and that's what we put in the burette. And we use that to find an unknown concentration. And that's called the analyte. And that's what goes down in your Erlenmeyer flask. So here's just a picture from your textbook of somebody doing a titration. Obviously, their solution is kind of this bluish, so it's most likely some kind of copper compound in the solution. And then to the right, you can see, zoom in of the burette. So for titrations, you need to know when to stop. That's what's known as the endpoint. And so we usually use some kind of indicator for that. Something that is somehow visibly going to be seen when you've reached the endpoint. For most acid-base titrations, which is the most common type of titration, use phenolphthalein, which will turn light pink when it is in basic solution. As I said, acid-base is the most common. But there are many other types. Right, if you're using a burette and if you're using it to find an unknown concentration, you're doing a titration. Let's just take a look at a practice problem. Again, this is just more stoichiometry. So let's say 25.00 ml of an unknown concentration of HCl is titrated to an endpoint with 17.24 milliliters of 0.150 molar NaOH. What is the concentration of HCl? So obviously for these types of problems, one of the things that you're going to need to do is have a balanced reaction. So this is a neutralization reaction. So we'll combine our strong acid HCl with our strong base NaOH, and then we'll form water, right, to neutralize it, and then a salt, in this case, sodium chloride. And then if you're thinking about the problem, generally with word problems, you want to kind of start off with what you want. And so if we think about what we want, it's the molarity of the HCl. And so the two pieces of data that we're going to need for that is the moles of the HCl over the liters of the solution of the HCl. Thinking about where we can start off with, right? We started it off, or we know the most about the sodium hydroxide. So you want to start talking about sodium hydroxide. And then the 17.24 milliliters refers to the sodium hydroxide. And it's not a conversion unit. So we've got that right there. You think about what else we know about the sodium hydroxide. Well, we know its concentration, but we know molarity is moles per liter, and we're in milliliters right now, so naturally you want to convert to liters. After that, we can use our concentration, so 0.150 moles over 1 liter. And now we're at moles of NaOH or moles of A. Whenever we want to go from moles of A to moles of B, we need to use our balanced chemical equation, our stoichiometric factor. So that's 1 to 1 in this case. So for every 1 NaOH, I get 1 HCl. Now I'm at moles of HCl. If I think about what I want moles of HCl on the top, which it's already there, and then I want liters of solution down on the bottom. I don't have that yet, so I can put my volume down on the bottom. In this case, the volume of the acid is the 25 milliliters. And then, of course, I want to convert that over to liters because molarity is moles per liter. And then I end up with molar of HCl, and I come up with 0.103 molar. So that's one way to do it. You can also think of it as like a plug and chug problem, right? You could try to solve for moles of HCl, which is most of that problem down there, and then solve for liters of solution, which you would just take your 25 milliliters and convert that to liters. Whichever way you want to do it is fine. We just need to have everything be nice and organized.